In this lesson, we'll cover the chain rule, which is a rule for differentiating a composition of two functions. I'm going to start by simply stating the rule. It says that to differentiate f composed with g of x, it's equal to f prime, the derivative of the outside function, of g of x, so you leave the inside function alone, but then you multiply by the derivative of the inside function, which is g prime of x. Let's apply this rule in example 1. To start with, I'd like to find this derivative without using the chain rule. How would we do that? Well, e to the 2x is the same thing as e to the x times e to the x. And the reason is, if the bases are the same, you can add the exponents. So to take the derivative of this thing, it's really the same thing as taking the derivative of e to the x times e to the x. So here we can use the product rule because we have a product of two functions. The product rule says you copy down the first and you take the derivative of the second, which is, well, just e to the x. You then add on the second and multiply by the derivative of the first, which is also e to the x. So here the derivative is, well, it's 2e to the x times e to the x. And since e to the x times e to the x is e to the 2x, you can simplify the answer as 2e to the 2x. So here, what is the derivative of e to the 2x? I'm actually going to write this as e to the 2x times 2. So using this approach wasn't necessarily difficult, but was kind of lengthy. And this rule, the chain rule, can actually make this a lot faster. So let's try this again. Take a second look at this problem. Okay, the way to use the chain rule is try to identify the composition that appears within this function. This is e to the 2x. I'll note that this 2x is being composed in the function e. So here the g of x is the same thing as the 2x. At this point, I'm just going to pretend I'm taking the derivative of e to the x. I know this is not just x, I know it's 2x, but the idea is just pretend you're taking the derivative of e to the x. And what's the derivative of e to the x? Well, it's e to the, I'm pretending, but it's e to the x. Now I go back and say, well, wait a minute. This thing was not just x, it was 2x. And the chain rule says, if that happens, you then have to multiply by the derivative of this thing. And what's the derivative of 2x? The derivative of 2x is 2. And so your answer is e to the 2x times 2. Let's note that this answer and this answer are exactly the same, which is a good thing. But let's also compare this to the chain rule. This e to the 2x part is this part of the chain rule. We took the derivative of the outside function, pretending the inside function was just x. So this part here is referring to this part here. But since this thing is not just x, it's more complicated, it's 2x, we had to multiply by its derivative, which is this thing here. And that's this part of the chain rule. So when you have a composition, you take derivatives like you normally do, but if the thing inside your function is not x, you then have to multiply by its derivative. So maybe just another really quick example. What's the derivative of e to the 5x? The idea would be, well, identify the composition g of x. The first step is take the derivative of the outside function. What's the derivative of e to the x? It's e to the x. Now, the thing inside the function wasn't x, it was 5x, and therefore we have to multiply by its derivative, which is 5. Let's practice this in a few more examples. In example 2, I want to differentiate these three functions. And just a reminder, we're using the chain rule for all three of these. The chain rule is used for when you have a composition of two functions. The chain rule says, take the derivative of the outside function. And if your inside function is not just x, but it's something else, you have to multiply by the derivative of that function. So, how would I take the derivative of sine of 3x plus 1? Well, what's my function g of x? What's the inside function? Here, it's 3x plus 1. So when I look at this problem, all I'm thinking at first is, oh, the outside function is sine. How do I take the derivative of just the outside function sine? Well, I know the derivative of sine is cosine, and the inside function stays the same. I then go back and say, well, wait a minute. The inside function wasn't just x. In fact, it's 3x plus 1. The chain rule says you then have to multiply by the derivative of just this thing. And the derivative of that is 3. So unsimplified, here's the derivative of sine of 3x plus 1. It's cosine of 3x plus 1. And this 3 came from the derivative of 3x plus 1. Let's try this with a cosine of x squared minus 4. What's the inside function? It's x squared minus 4. So at this point, I'm thinking, okay, we're just taking the derivative of cosine. And I know the derivative of cosine is negative sine. I know I have to copy down the x squared minus 4. Since this thing was not just x, it was more complicated, I now have to multiply by its derivative. So what's the derivative of x squared minus 4? X squared goes to 2x, the minus 4 goes to 0, so we can multiply by simply 2x. And that's it. A last one here. What about the derivative of e to the x squared minus 4? Again, the inside function is the x squared minus 4 part. So when taking the derivative of e to the something is e to that thing. But by the chain rule, I have to multiply by the derivative of that inside function, which again is 2x. So these are not simplified. I mean, they're pretty close, but I'll just leave the answers in this form. All right, so let's build up in complexity here. So we're still just taking derivatives of functions, but these are becoming slightly more complicated. I'm also seeing that I see a cosecant of x and a tangent of x. Maybe just as a reminder, if you take the derivative of a cosecant function, the answer is going to be negative cosecant times a cotangent. Likewise for tangent, if you take its derivative, it goes to a secant squared. So let's use those as a reminder later. To start with, I want to differentiate this first one here, x to the 4th plus 5x squared minus 8 to the 7th power. The inside function looks like it is x to the 4th minus 5x squared, plus 5x squared minus 8 to the 7th. So when I look at this thing, I'm really thinking it's something to the power of 7. How do I take the derivative of something to a 7th power? Well, I would bring down the 7, I would copy down the variable and subtract 1 from the exponent. So I'd copy down the x to the 4th plus 5x squared minus 8. However, this was not just x, it was much more complicated. This is where the chain rule says then you have to multiply by the derivative of just this inside function. The derivative of x to the 4th plus 5x squared minus 8 is 4x cubed plus 10x. Here I included parentheses because this entire thing has to be multiplied to this entire thing. Now, what about the derivative of the square root of 1 plus cosecant of x? Before taking the derivative of this, I'm going to rewrite it so it is 1 plus cosecant x to the 1/2 power. Written this way, I see the inside function is 1 plus cosecant x. So I'm really thinking of this as take the derivative of x to the 1/2. The rule for that is you bring down the 1/2, you copy down the inside part, which is cosecant x, and you subtract 1 from the exponent. And 1/2 minus 1 is negative 1/2. You now multiply by the derivative of 1 plus cosecant x. 1 goes to 0, and the derivative of a cosecant function is negative cosecant x times cotangent x. All right, we got one more here. What is the derivative of tangent of 1 minus x? The inside function is 1 minus x. So I'm just first taking the derivative of tangent, and its derivative is a secant squared, and we copy down the 1 minus x. By the chain rule, I have to multiply by the derivative of just 1 minus x, and that is negative 1. All right, so things are kind of getting complicated now because we have a lot of rules. Product, quotient, chain rule, and rules for a bunch of different types of functions. and they can all happen in a single problem. So here in example 4, I see we have a product in this part and a product in this part. So I have to use the product rule. So maybe just a reminder, the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. So I have to use that here and here. But at the same time, when I take the derivative of the second, it's a composition, so I'll have to use the chain rule as well. Let's try it out. Here's my product. It is x squared times e to the negative 6x. The product rule says you take the derivative of the first and you multiply by the second. You then add on the first, and now you multiply by the derivative of the second. And in the second, we have a composition of two functions. The derivative of e to the negative 6x is e to the negative 6x. But by the chain rule, you have to multiply by the derivative of negative 6x, which is negative 6. What about here in part B? Again, we have a product of two functions. We have this 3x minus 4 to the fourth times x squared minus x plus 1 to the fifth. So again, we're using the product rule. But also, in each part, there's a composition. So I'm going to have to use the chain rule twice. For this one, if we take the derivative of the first, so that's this thing here, I bring down the 4, I copy down the inside, and I subtract 1 from the exponent. So that's 4 times 3x minus 4 cubed, but I have to multiply by the derivative of the inside function, which is 3x minus 4, and that is 3. And then I simply copy down the second, x squared minus x plus 1 to the fifth. Now I add on the first, and I take the derivative of the second. And again, we have a composition. I'll pretend this is all just x. I'll bring down the 5. I'll copy down the inside part. I will subtract 1 from the exponent. By the chain rule, I have to multiply by the derivative of this inside part, which is 2x minus 1. And I have to put parentheses around it. So this whole thing is the derivative of this function. And here we use the chain rule 2 times. And the reason is I had a composition here and a composition here. Well, if it happens with the product rule, it'll happen with the quotient rule as well. So that is, if you have a ratio of two functions and you take its derivative, the quotient rule said it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And here I see a fraction. I'm actually going to rewrite this function as r divided by r squared minus 4 to the 1/2. And here I can see, okay, we have a composition of two functions. If I want to find dy dx, the quotient rule says simply copy down the denominator, which is r squared minus 4 to the 1/2, and then you multiply by the derivative of the numerator, which is 1. You then subtract off the numerator, which is r, times the derivative of the denominator. Okay, so looking at just the denominator, you bring down the 1/2, leave this alone, and subtract 1 from the exponent. So that's 1/2 r squared minus 4 to the negative 1/2, but you have to multiply by the derivative of this inside part, which is 2r. And then this whole thing is divided by the denominator, which is r squared minus 4 to the 1/2. This whole thing is squared. There is a lot of simplifying that you could do here, and I'll leave that for you to try, but unsimplified, this is the derivative of this function. Maybe just as a quick side note, this is not the only way to solve this problem. You can, without first taking a derivative, you can rewrite this function as follows. R times r squared minus 4 to the negative 1/2. Since this exponent is a positive 1/2, you can move it to the numerator, provided that you make the exponent negative. Written this way, you don't need to use the quotient rule, but you can use the product rule. Just to see what that would look like, dy dx, the derivative, is equal to the derivative of the first times the second plus the first times the derivative of the second, which is, okay, it's negative 1/2. Bring down the negative 1/2. Copy down r squared minus 4. We subtract 1 from the exponent. So negative 1/2 minus 1 is negative 3/2. And then you can multiply by the derivative of the inside piece, which is 2r. And unsimplified, this is the final answer. So here's where the composition appeared this time. These two pieces, these two answers are the same, even though they look different. You can simplify this one and show they are in fact equal to each other. Okay, what about the derivative of f of t is equal to the square root of this fraction, t divided by t squared plus 3? I'm going to write this as t divided by t squared plus 3 to the 1/2. And written this way, it's something to the 1/2 power. So when I take the derivative f prime of t, I'm pretending this whole thing is just t. I bring down the 1/2, I copy this down, and I subtract 1 from the exponent. But now, by the chain rule, I have to multiply by the derivative of just the inside part, which is this thing. Now, that's a fraction, so here again, I would use the quotient rule. The quotient rule says it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. There's a lot of simplification that could happen here. You can multiply this together, we can combine some like terms, we can make this exponent positive. I'll leave that for you to try, but unsimplified, this is the derivative of this function. All right, in example 6, one final thing that can happen when using the chain rule. Here, I want to take the derivative of 1 plus e to the 2x all cubed. And I'm going to just rewrite this so it's a little bit bigger. So that's the derivative of 1 plus e to the 2x cubed. Clearly, I have to use the chain rule because I have something cubed. So to start, you'd bring the 3 down front, copy down the inside, subtract 1 from the exponent, and then I would multiply by the derivative of the thing here. But wait a second. This thing actually has a second composition on the inside. And what this means is we'll have to use the chain rule twice. Let's carefully see why. To start this, I bring down the 3, I copy down the inside part, and I subtract 1 from the exponent, which is 2. I then start over and I say, okay, I now have to take the derivative of just this part. The derivative of 1 is 0, and I have to take the derivative of e to the 2x. But since this is also a composition, the chain rule must be applied. So I'd have the derivative of e to the 2x, which thankfully that's e to the 2x, but I have to multiply by the derivative of 2x, which is 2. So the chain rule was applied 2 times. First here for the first composition, but then also here for the second composition. You have to apply the chain rule for as many compositions that appear within your function. Let's see if this happens again in part B. So I'm taking the derivative of, that's sine of 1 plus cosine of 3x, and there's no exponents, it's just this function here. All right, we got one composition, it's sine of this thing, but within that, there's also this. Again, we have 2 compositions. I am anticipating using the chain rule 2 times. To start with, I'm taking the derivative of just sine, which I know goes to cosine. Cosine of all that stuff. 1 plus cosine of 3x. But then, by the chain rule, I'm focusing on just this part. Now I'm taking the derivative of just this. The 1 goes to 0. The derivative of cosine of 3x, well, first, it's negative sine of 3x. But by the chain rule, I also have to multiply by the derivative of 3x, which is 3. So again, here, this negative sine of 3x came from the first composition, and then this 3 came from the derivative of the second composition. The last thing I'd like to consider for this section is we have two different notations for taking derivatives. We can use a prime, or you can write a dy dx, for example. And for this reason, there's another way to express the chain rule, and it's written this way. Dy dx is equal to dy du times du dx. This statement says the same thing as if you're taking the derivative of a composition of two functions, you first take the derivative of the outside function, which is f prime of g of x, but then you multiply by the derivative of the inside function, which is g prime of x. It looks very different, but the thing that is sitting right here in this formula is the same thing as this first piece. You're taking the derivative of the outside function. But if you have a composition, you also have to multiply by the derivative of the inside function. Let's try using this in example 7. Here we have the function y is equal to the cube root of 1 plus 5x. First, I say we just try the old way. If you want to take the derivative of this function, you're taking the derivative of 1 plus 5x to the 1/3 power, because a cube root is a third power. The chain rule says you bring down the third, you copy down the 1 plus 5x, you subtract 1 from the exponent, which gives us negative 2/3, but then you have to multiply by the derivative of the inside function, 1 plus 5x, and that gives you 5. And that's it. Unsimplified, you can leave your answer like this. To apply this other notation, I'm going to rewrite the function y is equal to 1 plus 5x to the 1/3, and I'm going to define a function u, and u is the inside function, which is 1 plus 5x. If you write it this way, then y is equal to u to the 1/3. And so it's kind of like we have two functions. Y is equal to u to the 1/3, u is equal to 1 plus 5x, and if you compose these two things together, you get this. Well, I guess first, what is the derivative of u with respect to x? So that's taking the derivative of this equation here. Well, if you take the derivative of u with respect to x, the answer is just 5. All right, 5. Also, we're going to take the derivative of y, but not with respect to x, but with respect to u, like this. That derivative is 1/3 u to the negative 2/3. Written in this notation, if you want to take the derivative of y with respect to x, it's the product of these two things. That is dy dx, it's equal to dy du times du dx. And we just computed both of those things. Dy du is 1/3 u to the negative 2/3. Du dx is 5. If you want your answer completely in terms of x, you can resubstitute 1 plus 5x in place of u. And that gives you 1/3 1 plus 5x to the negative 2/3 times 5. And what do you know? This piece here is equal to this piece here, and this piece here is equal to this piece here. So you can use either of these notations when taking the derivative, but we're really doing the same thing.